Thank you very much, Shafiq. And I would like to draw your attention. This is the session for session 22 and for TC 22. And I must, right on the onset, praise the effort by my colleague Abdul Malek Sikder from IEB. And I'll request him to join me uh, here because he's the one who has been organizing and doing all the hard work. So please, thank you very much. Our first presenter for today is from Myanmar, and it is the evaluation of seismic hazard map of Myanmar using updated PGA data and regression analysis by Y.R. Aung. So may I request the presenter, please? Uh, no, may I, sir, sorry to interrupt, but you have 15 minutes, and it'll be followed by 5 minutes questions. Thank you. That we got from the previous uh, this is the feedback format, which is very hard for us, right? So that I'm not saying can give the rough summary. The user can uh, the user can get the data by his coordinate. So uh, the user can know or we are open for any questions. Anybody would like to have a question, please? Any question from the audience or the people who are attending this session online? All right, it seems that there is no question, but I have a small question, sir. What was the reason that you have converted it from 475 to 2475? Because in our design code, we use mainly we use this ASC. ASC is in the UV 97 we use the PGA data 0.2, 0.4. In the ASC context, we the spectral acceleration is based on SSS. That's why, and also the its acceleration is for MC level, and then they convert it into PV level. So that's why if we have to follow this trend, we have to convert it our PGA SSS. That's why we convert. Yeah, but the normal standard practice is to use 475 years return period for the ordinary buildings that we use. 2475 is for essential and critical infrastructure like dams and other things. Yes, yes, we can adopt. Yes. Thank you very much. Any other question from the colleagues? All right. Thank you very much. Thank you. It was an interesting presentation. Today's second presenter is my very dear colleague, Muhammad Shafiul Islam from Institution of Engineers, Bangladesh, and he'll be talking about seismic assessment of existing RC buildings in Bangladesh, a correlation between visual rating method with detailed seismic evaluation method. Shafiq, they're all yours. Thank you.
Good afternoon, everybody. Welcome to my presentation on the seismic assessment of existing RC building in Bangladesh, a correlation between visual rating method and detailed seismic evaluation method. So, yeah. So, in Bangladesh, there is large stock of seismically vulnerable buildings. So, it is very essential the detailed evaluation of existing all of buildings to make the CC seismically resilient and also to save the life and reduce the loss of damage or something like that. So that's why. Since we have lots of seismically vulnerable buildings, so it's very difficult to manage all buildings together. That's why, because of we have limited experts and also budget also and other issues. So here, so therefore, we developed several methods like a rapid visual screening method and also detailed evaluation, so that we can do some prioritization and simplification of like the prioritization of the existing building before detailed evaluation. And here, that's why we had last 12 years or 13 years, we have several research projects and technical cooperation projects by JICA like CNCRP, BSPP, and SATIP SWIP projects, and also UBSP projects. And from these projects, supported by JICA Technical Cooperation, we developed several manuals for evaluation, sorry, for seismic evaluation and also retrofitting and also urban planning strategy. And those manuals works together in Bangladesh. We are now using those manuals, and those manuals is developed by PWD, Ministry of Housing and Public Works in Bangladesh, supported by JICA. And first of all, I'd like to talk about a little bit VR method, visual rating method. Actually, this method is a simplified way for predicting the seismic capacity by using simple column area, measuring field area, and number of story. Actually, and the purpose is to set the priority for detailed evaluation. And here we use this method for large building stock, and then we will categorize the building A, B, C, D, E. Here different category, and then we will set the priority for detailed evaluation. Actually, I'm not going to tell about detail about this VR method, because last ECM in 46 I only talk about the VR method, and today I'm going to talk about more detailed evaluation method, and also some correlation between this VR method and detailed evaluation method. And my next presenter will also talk about little bit about the VR method. And now detailed evaluation method here. And I already talk about there is first the CNCP manual we already developed in 2011 to 2015 project. And then in that manual, we have some limitations. These are the common feature in Bangladeshi buildings. So low construction quality, and also state anchorage river issues, and also effect of infill wall, and also high axial force, narrow column size, and also narrow beam column joint. And those are the common feature in Bangladeshi buildings. Actually, that's why we did some research, and we did some study by help of JICA and the Japanese University. And then today I'm going to talk about the effect of infill wall, because the effect of infill wall is very important. It's changed the strength and also ductility of structure. And here I'm going to talk about the evaluation guideline. Here, this seismic evaluation guideline is developed by the SATTEP SWEEP project, which is supported by JICA, Japan. And here there is 6 chapters, you see. And here all chapter is very difficult to explain everything into the session. So if you are interested, you can download this manual, and you can use, and you can go through, and you can apply in your country. And today I'm going to talk about only chapter 4, RC frame with mesh infill, because many of the structure, most of the structural system is masonry infill with RC frame. That's why I'm going to talk about how to evaluate this structural system. When we design a structure, we just consider as a frame only. When we design as a structural engineer, but reality, there is masonry infill inside the frame system. But after earthquake, what happened? This is the Nepal earthquake, and here you see that this masonry infill changed the seismic behavior. Because before, during the stage, we considered only frame, but reality, masonry infill, and then the seismic, the masonry infill completely changed the behavior of the damaged building. So this masonry infill wall is not considered as a structural wall when it is designed. But if we consider, if you see this figure, this is just a quality figure. If you see the RC bare frame, this is the force deformation curve. And if we consider the masonry infill with RC frame, then strength is also high, and also ductility also increased. So why we not consider this advantage of the masonry infill frame? So that is the point of discussion actually. And here, if I see actually we are adopting Japanese seismology standard. This is the Japanese standard 2001, and then we developed this manual by PWD. And here the basic idea is that this is the infill frame, and we consider two RC frame and also masonry infill. So together we calculate the C index and F index. And this is the seismic index, what we calculate after the seismic evaluation of the existing building. And in the following slide, I'm going to talk about very briefly how to calculate this C index and F index of masonry infill frame. And here, this is the flow diagram. So first of all, we have to check is it a structural, non-structural wall, and then structural element, and then non-structural element. And then we will judge the strength index and ductility index, and then we will of course check the out of plane failure. So if the wall is out of plane failure, then we will not take in consideration about the strength. And first of all, classification in the structural wall. So here this structure wall, is it for example this wall, is it structural or non-structural wall? Then we can just two condition here. One is confined, it should be confined with RC column and beam. So this is beam and this is column. So it should be confined with the RC frame. And another condition is that H infill divided by T is less than 30. This is two condition so far we are considering as it is a structural wall. And in case of opening, there is also some reduction of the strength because of the opening here. Opening area, if it is less than 40%, and there is three condition. And also this wall, so far we are not considering as a structural wall, because if you see there is opening here, and also here is opening, and also here is opening. That's why these walls so far we are not considering as a structural wall. It needs further some research to consider as a structural wall. And here, another point is we use solid bricks in Bangladesh actually for as a structural as a wall masonry infill wall materials. So hollow block and hollow concrete. If we want to use these types of material, we need to do further research and study analysis. So first of all, we have to check the judgment of the failure mode. What types of failure mode of this the masonry infill wall? So we found from analysis and research by these SATTES projects, there's four types of failure mode, like diagonal compression failure, sliding, overall flexure, and column punching and joint sliding failure. If you see these four types of failure mode, so so far we found these four types of failure mode during the earthquake or during the experiment or something like that. So if you see the diagonal, this diagonal compression, and this is compression and sliding, and this is overall flexure failure, and this is here punching, column punching, and also here is a little bit cracking. But we need to understand how to evaluate this failure mode, because if I consider as a design stage or the evaluation stage, I need to check the failure mode first. So here we consider a parameter to failure mode. Here beta index. Here the column lateral strength. So this column and this column, we have lateral strength and also infill lateral strength. So this is infill, this is infill lateral strength. So this is ratio. This ratio is simply can calculate the difference or judgment of the failure mode. And here we just make some matrix. We made this matrix. The difference of failure mode is beta is greater than 1, then type shear type failure and flexure type failure if column. And also it depends on the column size and also short column. And also here this duration is the difference of the failure mode. Now strength index. How to calculate the strength index of these four types failure mode? And here the strength index can be calculated by using this equation. So this is Q mu equals to nothing but is the lateral force, total column and masonry infill, and weight of the building. This is the ratio. This is the index CMW. And actually these equations actually comes from several research and experiments. So if you want to learn more detail, you may go through this manual. And also there are a lot of references published in the different journal paper. So you can go through. And this is type 1, type 2 failure mode. We found this, we developed those equations. For diagonal cracking, we have to calculate the Q, and also for sliding, we calculate Q sliding by using these equations. And another one is overall flexure also. It is like the RC column, this M divided by H. And also this punching shear strength in case of this failure mode, column punching and joint sliding failure mode. So this is how we calculate the strength index of these four types of failure mode. So we need another important parameter, that is ductility. How to calculate the ductility of these four failure modes? So we just developed based on analysis and research. We considered the ductility index, that is F index 1.75 for diagonal compression failure, and sliding and diagonal cracking in that case 1.27, and overall flexure failure 1.75, and punching is 1.27. So in this case, we can see that if the frame is failed by diagonal failure, then ductility is very high ductile behavior in case diagonal compression failure, these types of failure. But in case of this type failure and this type failure, only 1.27, so less ductile behavior of this frame. So this idea and concept we applied several existing buildings in Bangladesh. And if you see, we surveyed 22 buildings in Dhaka city. Buildings are located here, these buildings, and those buildings are wide range in the construction, year of construction 1993, before and also after 2006. And during this survey, we applied VR method, like visual screening method. This screening actually I choose because I already showed in last year presentation in my these slides, and this is just a simple method. And this data sheet we used in VR method. My next presenter will talk about little about this document. And there is some visual inspection of buildings, and this is the 6 to 8 buildings in Bangladesh, residential buildings. And this is, you see the narrow column size. And here we did some NDT test, like a core cutting test, and also rebound hammer test. We consider we applied during the investigation. You see this figure. Here is sketch test. We consider to try to understand the column strength, column concrete strength, and also rebound hammer test. And we calculate the detailed evaluation like IS shown in the previous slides here by considering the PW manual also SWIFT guidelines together. Here we calculate the IS index, and also we calculate also IVR index here, IVR index, and then we finally found here the horizontal line is the visual rating index, and here the vertical line is IS index, seismic index, detailed evaluation results. And then you can see there is very good correlation between the seismic index and visual rating index. So VR index, maybe if I can explain a little bit more, then you can understand what is the visual rating index. So, but their time is very limited, so that's why. This manual and so this manual also are in the website, so you can easily download, and then you can read. And if you have any question, you can email to me, and then I will give answer. So the point is that we need a little more time to calculate this seismic index IS2. But if we can conduct the visual rating method, so we can understand what is the seismic capacity. So this visual rating index can understand the seismic capacity index of the building without detailed evaluation. This is just approximate estimation of this the seismic index. So this is that the correlation that developed in this research and study. So this is the summary of this presentation, and here we already developed here method, and we already understood that the visual method has good correlation with the seismic index. And also we observed that about 50% building needs detailed evaluation, because if you see the previous slides, if you set some boundary here, like 0.45, then 50% building, it should be required the detailed evaluation of this building. It's very urgent needed. And also finally, we can say that this VR method estimates good judgment as a seismic capacity of existing building. So that's all from my presentation. Thank you very much.
Once again, Shafiq, thank you very much for a wonderful presentation. We are open for questions, suggestions, comments, please, from the people present here and online. Sir, kindly introduce yourself and then the question.
I'm Shepherd from Fed IBS. I'm P. Mao. So I have a simple two question, and one question is to address the where can I download for your highlighting the practice and code. Yeah,
Jaika.
JICA. Yeah, the website link. Where can I download the website link?
Oh yes. Oh, I see.
Yeah, yeah.
Uh,
So that's the question one, and question two. So now you address for the structure infill wall. So how about for the placement, the good practice and the good standard for the placement of the linter and the stiffener? The linter and the
Lintel.
stiffener. Yep, yep. Because of I didn't notice at your infrastructure wall all the way up just brickly up. So what is the good practice for placing of stiffener and linter?
Actually, in our country, we use lintel in the window level.
So
Window.
so let's say so the walling height is about 11 feet. So do we need to use a stem linter?
No, we don't need actually.
Oh,
But if column
still,
size is very high,
yep,
then we need
yep, yeah. So
stiffener.
what was the standard height?
Standard height, it depends on the defined code. So in Bangladesh, 50 half. If there is window, we put lintel just on the window, above the window and door.
So if there if yeah,
Location.
yeah, yeah, the RC building.
Just put on the window.
So about
If we provide continuous lintel, that is going to create short column effect. So we nowadays, after getting some knowledge, we avoid providing the continuous lintel. We just construct the beam column framing system and the lintels just on the door and window, piece, small pieces.
so let's say for the 14 feet height, yeah, do we no need to be thinking about for the those kind of linter beams, right?
Are you talking about the
14
masonry
feet high.
wall height?
Yes, yes.
So you are concerned about the masonry infill?
Yep, yep.
Okay. There are two things. One is the frame and other part is the masonry. The stability, you are concerned about the stability of the masonry wall. But yeah, for this, if it is 14 feet, you have to provide intermediate lintel. But again, you have to be very, very careful. You have to analyze the RC frame accordingly, and which is not that easy. To to analyze a concrete frame building with masonry infill in your model is really difficult. So you have to be very, very careful.
Thank you.
Kindly introduce yourself first.
This is Subhash Chandra Baral. I am from Nepal. I'm president of Nepal Engineers Association. I think I want to clear what he's trying to ask. He's talking about the band in the wall, I think.
Lintel.
So yeah, the lintel. I normally after the Gorkha earthquake in Nepal, 2015. Normally we use before that we just use the wall in the. There is no any provision or something that in the code also, I think. The wall you can construct at any height. Now what we have a provision that you must have a band in the, at least if there is no any opening, then you should have a band at least at 4 feet. With height of 4 feet, there must be have one band, continuous band in the masonry wall. And in the, if there is an opening, then normally if there is a window, then just below the window and just above the window, there is a the band throughout the wall. We are practicing this one after the Gorkha earthquake. I think he's talking about that. Yeah. And one more, one question for the presenter, that you just mentioned that you are just assuming that this infill wall can be the part of the structure, I think.
Yes.
Yeah. Then what is the difference that is the column or beam or this frame structure is customized or the optimized with this consideration, or if there is any value that you can optimize the cost of this frame? Did you find any figure?
You mean you're talking about?
I'm talking about, you are just considering that infill wall can be the part of this structure, yeah?
Actually, from wait, moment.
Yeah. Just I want to know if you are considering the infill wall as a part of the structure without infill wall and with considering the what is the difference in there?
Yeah.
Now, there are two things that we must be very careful about. You know, in our part of the world, especially Asia and Southeast Asia, a lot of buildings are non-engineered and they're load-bearing, unreinforced masonry structures. So we built a wall and then put a slab on it, and then we have several stories, maybe 2, 3 stories. If that is the case, then the walls have to be bound together, and this is with the concept of bands or lintels at the sill level and at the roof level are essential. But in this case, the case which my friend from IEB was talking about, is talking about medium rise, reinforced concrete, framed structures. And these are designed, whether deficient or not, to resist the gravity loads only, and some of them may have some seismic resistance. Now, since the building is already there, even though it was not designed for the masonry to take the lateral resistance from the earthquake, but since the masonry is there, when we are doing the assessment after the construction, then these kind of exercises are important because they are going to provide certain level of lateral resistance. And that is what Shafiq was trying to point out, that there is a non-structural element which can contribute to the structural load distribution also. But when it comes to designing the buildings, and if it is a framed structure, we don't normally take the masonry because masonry is brittle, and at some stage it can crush. And that's the mode of failures that is spoken about. So these were the two things. But this is for an existing building, where the masonry is already there, we can make use of that particular non-structural element. I hope I was able to.
Yeah, yes.
No.
Actually, I just want to add, during design stage, actually we don't consider masonry, like lateral force, because we have to, for the mid to high-rise building, we need to calculate the lateral force, right? Lateral force, we just consider column and also RC wall or something like that. But masonry wall, we don't consider. But when during the earthquake, after earthquake, we found that this masonry infill changed the behavior. Like column should be hinged, like here. Here column should be hinged, but sometimes column hinge is other place or something like that. So that's why we are not taking the advantage of this. So there is some advantage, of course, for this masonry infill. It increase the strength of the building, lateral strength especially. So that is the point.
Any other question from the colleagues? Yes, ma'am.
Thank you. I'm an architect, so my question will be a bit different. So I'd like to know if there is any difference when you design the building, just post and beam without infill. What is the difference in its strength in case of earthquake compared to the structure with infill wall?
I see. So could you go the first slide? Second, just no. Just first slide. First, second. Number one. Uh, down, 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 down. This one. So this is might be maybe because uh, when we design of a building, we just consider bare frame, right? In case of bare frame, if we push here, like earthquake, push, and then this is the common behavior, like strength and ductility. And if we put the masonry infill, and if we push from this side, then it like this way. So if you see this is the strength, this is a strength, and this is the story depth, ductility. So if change this strength huge, sometimes 2 times increase the strength, and also sometimes ductility also a little bit increased. So this is the change of the behavior. if we consider masonry infill. So this is the advantage of the masonry infill. Is it okay?
Yeah.
The answer?
Yeah, thank you. How do you connect the brick infill with the RC column? Is it just how do you connect structurally? How do you connect the
Well,
infill
it is
with
just the normal, like mortar,
just
only
mortar?
mortar.
Just mortar.
Just mortar, yes,
Oh,
yes.
okay.
But this is a common practice in Bangladesh.
Yeah.
Just we put mortar.
Yeah.
But in case of out of plane failure, maybe we have to, if we put some other technique, maybe it is helpful to prevent the out of plane failure, something like that.
Thank you.
Mhm. The design stage. Yes, yes. Actually, maybe this already sir already given this answer. Because you know, especially the old building, the column size is very narrow. Oh, new is okay. Yeah, yeah. This is actually, this is for the, yeah, yeah, yeah.
I I
Yes.
would not, I'm sorry to intervene, I would not recommend that. The reason is that the walls are non-structural and we tend to change them. Sometimes you punch a window, sometimes you punch a door, sometimes you remove the wall,
Mm.
and you cannot put a writing on the wall that this wall is not supposed to be removed. So that is why the strength is there. It's kind of a reserve strength, but
These are strict. Mm. Yeah.
Thank you, Shafiq. Thank you
Thank you.
very
Very good
much.
question.
It was an interesting discussion, but I'll request that if you have any further question, you can contact him directly.
Thank you very much.
Thank you very much. Our second presentation is also from, is also from our friend from Institution of Engineers Bangladesh, my very dear friend, Mr. Abdul Malik Sikder, who will be talking about a seismic vulnerability assessment of existing buildings in Bangladesh towards an optimal strategy. Reggie, we're all yours.
Good afternoon, ladies and gentlemen, and thank you, Mr. Chairman. In my presentation, I'll briefly try to introduce what we have been trying to do in Bangladesh, specifically in the Public Works Department under the Ministry of Housing and Building Construction. So the title is a seismic vulnerability assessment of existing buildings in Bangladesh towards an optimal strategy. As a very old organization in PWD, we have got a huge number of vulnerable buildings. When I was a superintending engineer in the design, that I found a huge stock of buildings uh, around less than 6 story, masonry and RC frame structure, very old, 42, even more than 100 years. So we were thinking what to do with these buildings, how to assess and how to retrofit. And we did not have the technology at that time to assess these buildings properly and to retrofit. So we were searching for technical assistance who can really help us. Finally, we requested the Japanese government to assist us in acquiring those technology. That is the way some projects started with JICA assistance. And you know about the seismicity of our country. These are historical earthquakes in and around Bangladesh very large earthquakes over the last more than 100 years. And one of them is 1897 8.7 Great Indian Earthquake. That was somewhere near here. And that caused tremendous damage in the Bangladesh, India, Nepal, everywhere. And in Bangladesh, all the masonry buildings all over the country were destroyed. Of course, there were few masonry buildings at that time, and only maybe 1 to 2 story high only. So, what are our problems? Why we were searching for a method when there are different methods available in all over the world? Because of the specific characteristics of our own buildings. A large of stock vulnerable due to non-adherence to building codes, seismic design and construction practice. That is the main reason of the vulnerability. And of course, because of their distinct features, the assessment and retrofit techniques utilized in other countries cannot be directly applied to Bangladesh building. And Shafiul, my previous author, has explained this. So the problem, so when we started that project, we tried to go in deep the problem, identify the problem. The basic problems are the low strength concrete, narrow column size, no seismic detailing, part infill wall, and partly filled, partly narrow joint and 90-degree hook, those kind of things. And in a nutshell, this was our initiative. Starting from 2011 to 2023, we had 1, 2, 3, 4 projects. And out of those 4 projects, subsequently one after another, and this test sweep project, that was a 5-year-long research project. And through this project, final outcome was the seismic evaluation manual and seismic retrofit design manual was prepared, and we tried and we started applying these manuals. And while started using these manuals, we came up with lots of problems. In the real life, we found many problems. So to overcome those problems, we started that 5-year-long research projects. 4 Bangladeshi university and 4 Japanese university collaborative research, utilizing the labs in the Japan and also in Bangladesh, were carried out, and the final outcomes were provided in these 2 guidelines. And those 2 guidelines actually supplemented our original manual. So those are the 5 guidelines prepared in the research project. All those manuals are available in the website of PWD, free to download. I told you earlier that the original manual and the research manual, they supplement the original manual. And the limitations of our original manual were that the RC frame building with masonry infill was not there. Therefore, we have to do some research. And the lower strength concrete, the methods that we were customizing for us, for our country, those are the original Japanese standard. The low strength is not there. So therefore, we have to carry out some research. And at the same time, flat plate building. You know, in Japan, there are no flat plate building. But in our country, there are many existing non-engineered even flat plate building. So how to assess those? Therefore, we did that research. In that research project, we did research on that. And finally, we came up with this 4-tier evaluation method. Originally, though these 3 were not there, we could develop the detailed seismic evaluation method first. And when we started implementing that standard, what we found that we don't find any drawings of the existing buildings, no data available. So how to evaluate without any data? That's why we developed the simplified evaluation method. Only rudimentary information gathered from the owner of the building, we can carry out this simplified evaluation method. And with some added building survey, we developed one advanced simplified evaluation method. And again, as the number of existing buildings is huge, so we try to develop one rapid screening method. That's why this visual rating method came up. And you can ask me, why there's this new method? And we tried different methods available, but those methods don't really applicable in our condition. And for visual rating method, that was developed through that research project. And this VR manual was published. And about the visual rating method, this is a very simplified, rapid screening method, very simple. You can complete a 6-story simple building to assess it within 30 to 1 hour, 30 minutes to 1 hour, you can finish. Very simple and straightforward method. The information requires are minimal. So number of stories, column size, span length, number of walls. But visually and measuring only those rudimentary information you can assess. And these are the judgment criteria. The buildings are categorized A, B, C, D, E with least priority. A is the least priority and subsequent E is the highest priority. So if your building is found E, so highest priority should be given to that building. This is the VR manual guideline. This is the typical form to collect information for visual screening method. And the simplified evaluation and advanced simplified evaluation that I told you earlier. And here we calculate the seismic index for service load and seismic demand index, service load demand index we calculate, and the judgment is whether the demand index is the seismic index and service index, whether it is larger than the demand index or not. Based on that, so we have to decide to go for detailed evaluation. And if it is the seismic index is larger than the demand index, maybe it will be safe. And for simplified evaluation, those rudimentary informations will be required. And this concrete strength, it is assumed based on our research. And in case of advanced simplified, we have to carry out some building survey, including Schmidt-Hammer test, to know the concrete strength, and also the column size with reinforcement detail. We can really collect it, then we can go for the advanced simplified method. And finally, the judgment for is in a matrix. So service load capacity here and the seismic capacity here. From this matrix, if where is your building, and that will say the capacity, final capacity rank and recommendation. So if the building is in the zone 1, may be safe. If it is in the zone 2, detailed evaluation is recommended. And if it is in 3, so immediately detailed evaluation should be done. So the thing is that visual rating, AC and AAC are not conclusive methods. Those are used for screening purpose only, to make the list smaller, so that we can do the detailed estimation or evaluation for the least number of buildings. We can concentrate on the really vulnerable buildings. This seismic index method for detailed evaluation, which was explained in detail by my previous author. So we did some test work during our 1 decade of long research and development initiative. So what we did some test work to gain some experience first before we start retrofitting the actual building. So we did column jacketing, RC shear wall insertion, RC wing wall insertion, seismic slit, steel frame bracing, and carbon fiber wrapping. RC column jacketing through beam column joint, those very weak, narrow column and beam column joint. RC beam jacketing. External steel frame bracing without disturbing the activities inside the building. We can provide this kind of external steel frame bracing. And again, as we didn't, sorry, as we don't have any idea and data and experimental records of the existing buildings in our country. So what we did, we took up a very small testing program. So we prepared test specimens, 7 test specimens like this, bare frame and infill masonry, including infill masonry. And we tested, lateral load testing was done. And finally, we got these load deflection graphs defining the properties of all those frames. And as initially we did this pilot retrofitting of few buildings. One of the building is this. This is a small fire station building. We inserted steel frame bracing. We inserted RC wall, column jacketing, and ferrocement lining on the masonry wall. This is another building, 10-story building. What we did, we have added steel frame bracing, external steel frame bracing, keeping the day-to-day use intact without affecting the daily work. This is a public building. We provided external frame bracing, and also internally we provided shear wall here. By this way, we retrofitted this public building. So that way, we had a very good and a successful technical collaboration between Bangladesh and Japan. 4 universities of Japan and 4 universities of Bangladesh, they had a good cooperation and did that research work. And out of that research work and the initial project, we developed the manuals. And in PWD, we are using those manuals now and assessing and retrofitting the existing public buildings. So finally, concluding remarks. The seismic assessment and retrofit method developed by PWD Bangladesh, which is based on the Japanese method, has proven to be easily shareable among practicing engineers. We were really emphasizing on that point because we thought that the large number of engineers involved in the consulting sector or in the public sector, so they should be trained and upgraded their technical capacity within a very short period of time. That's why we developed these methods, and with the help of or based on the Japanese methods. Of course, there is potential for further enhancement of this method through ongoing application and research. This method could be relevant in numerous developing nations with comparable building features. And the last point is that PWD Bangladesh is prepared to offer technical support to the FED MES, and upon request will train their engineers in the assessment and retrofitting of existing RC buildings in Myanmar. Thank you for your question.
Thank you, sir, for a wonderful presentation. We have time for a couple of questions. Please. Yes, sir.
No. These are for existing buildings, not damaged buildings.
Oh, I see.
Yeah, our priority was to assess the existing buildings. We did not think about the post-damage earthquake. Post-earthquake damage assessment, we did not do that. Maybe in future, we'll go for that.
Okay, thank you.
After the Sagaing earthquake, maybe after 100 years or more, this is the largest earthquake that happened in that area. Yeah, people forgot about the severity of the earthquake and the damage. Yeah. So we are really concerned about that. That experts say that it is overdue to have a very great earthquake affecting our country. We are really concerned about that. But you know, it is very time consuming and difficult and very expensive to assess and retrofit existing buildings. Thank you.
So any other question? Yes, sir.
Again, this is Subhas from NEA. Very informative presentation. Thank you for this, for the Bangladesh team. My question is, you have a very good document. You have work hard for preparing all these documents for the engineers. In Nepal also, we are just working hard for preparing all these documents. And we have some good achievement on this for the document. But the challenges are this to implement in the community or to implement in this. And then the government also do not much prioritize on this result. So what is the status in the government in the Bangladesh for the future, for reducing the future vulnerability or the loss to implement all these documented all these document which you have been prepared that how the government prioritize it and how the engineering communities you disseminate to the engineering community and how much they are aware about this all this knowledge which you have prepared in the document. Thank you very much. Because
I
want
think
to
your
I want to
question,
know.
you have answered your question. Yeah, from a developing country like Nepal, Bangladesh, and Myanmar, the case is same. And our government, they have good intentions. They have all the support us, provide required funds, maybe not required funds, but small funds, partial funding is available. But for real life retrofitting, which is very, very expensive and time consuming, that is very difficult to get the required amount of fund from the government. So we have proposals submitted to the government, and depending on the priority of that building, government sanctions the money and PWD goes for retrofitting. As for example, PWD has already retrofitted a few hospital buildings because of the priority. And there are many, many hospitals which are really vulnerable. 5-story down, very old, vulnerable buildings. So, but one thing is that I really appreciate your saying that the collaboration that I know in Nepal, the Nepalese engineers are doing something, but what you really are doing, I don't know in detail. And at the same time, what we have been trying to do, you see, the 1 decade of effort that we are going through, I don't think that you know about this. So why don't we really cooperate with each other so that we can learn from each other? And in Myanmar, I don't know what you do in case of existing buildings. What is the technology you utilize, or do you have the technical capability to do this kind of assessment and retrofitting? So we could really learn from each other. So we should have a cooperation or a platform for cooperation. So we should try to develop that platform. And ACECC is one of that kind of platform. So we should come forward and try to utilize that platform.
Please, may I ask you two terms of this topic? Yeah, thank you. Base isolation and story displacement.
Are you talking about base isolation?
And story displacement. This, I request you please explain me this conclusion remark of this earthquake article I read in this morning. 1, 2, 3, 4 is I understand, but this
do you have any base isolation project in your country?
Yeah.
Yeah.
This article
Is it under construction or already done?
already done. This is damping. Yeah.
You see, a base isolation is normally done in a newly constructed building. While you're constructing the building, you put in the dampers and all those things, whether it's a BRB dampers or the base isolation rocker site dampers. But in an existing buildings, cutting down the foundation, raising up the building and putting the base isolation is an extremely expensive business which required very precise engineering. And there are very few buildings that I know of who have been base isolated after the construction. One of the hospitals in Turkey, in Istanbul, that I know of, I visited the site also, and a few buildings in the United States, especially the University of California Library building, which was a little more than 100 years old, was lifted up, and then this. But otherwise, it is extremely expensive if you're doing a retrofit. But if you're building a building itself and building a base isolation, then it's still expensive, but not as expensive as previously. Great. So thank you very much.
Thank you.
Thank you, everybody. You know, we had some very interesting presentations and some very interesting question answer session, but that leaves me with only 20 minutes. So I'm the last one to present, and I'll try to be very quick. I'll try to be very precise, but I'm sure that what I'm going to talk about is slightly different from my colleagues. They have been talking about micro level building assessment and retrofits and strength reserves that could be used for for the buildings, existing buildings. What I'm going to talk about is a macro level planning tool where you take the stock of a building or a region or after a particular earthquake or before a particular earthquake, and then we can perform a risk assessment of what are the risks of failures and what kind of failures the building can undergo. And I'm going to very briefly, even though I have 30 some slides, but I'll try to do it very quickly so that we'll be left with some time for question answers also. And I'll be talking about the understanding of earthquake risk in Pakistan, evaluating the vulnerability and the resilience of the built environment of Pakistan. And this study was conducted by me and one of my younger colleagues, Dr. Mohammed M. Can I have the clicker, please? Yeah. Yeah, this one. All right. Now, what is risk assessment? The risk assessment, as I told you, it's a wonderful planning tool, which for a particular area, for a particular region, and even for a country, we can do a risk assessment that in case of an earthquake, what will be the kind of damage expected? And if that is the kind of damage expected, what can be the strategies to improve the conditions? And then what are the policies that we can do to avoid a catastrophe? Obviously, the damage in an earthquake is something that we cannot avoid, but we can minimize and mitigate the damage during an earthquake. Yeah. So the basic concept is very, very simple. There are two things that we have to evaluate separately, and then we overlap them and see what is the amount of risk involved. One is the hazard. What is the kind of hazard that these buildings, and when I talk about hazard, I'm talking about earthquakes in general, in particular, that what is the possibility of an earthquake and what magnitude earthquake and what are the intensities in an earthquake that are possible in a particular region. And then we determine the exposure. Exposure is the number of buildings which are there, which are at risk, and then we evaluate the vulnerability in the buildings, how weak or strong they are, and then we overlap them and do the risk assessment and see how many buildings will go under damage and what kind of damage that we're talking about, whether the damage is going to be beyond repair or repairs are possible. And for that, I've taken the case of Pakistan, and it is unfortunate that the entire ACECC community, there's 17 countries so far, and out of those 17 countries, I think Australia has probably the least seismic risk. Other than that, you look at any other country, and it is under severe seismic threat, whether it is Indonesia, Malaysia, Pakistan, India, Bangladesh, Myanmar, or any other country, even the US and New Zealand. So we are in a region or in the area where we have tremendous possibilities of earthquake, and in our lifespan, we have seen some major earthquakes also. And a very recent unfortunate incident was on the 28th of March. And similarly, if you look at Pakistan, you can see that these red dots are the seismicity of Pakistan, and you can imagine that how many earthquakes has taken place over the last 200 years. And Pakistan is divided between the Eurasian and the Arabian plate, the Eurasian and the Indian plate, and this plate tectonic boundary on the eastern side also passes through Myanmar. So we share a common seismic threat. In the recent years, we have two major earthquakes. One was in 2005 on the 8th of October, and 73,000 people died. And then we had an earthquake in 2017, but luckily this was a very less populated area. However, there was a significant damage. And the other parts of the country are no less vulnerable. So, the importance, I think I've already spoken about. So in order to do that, we have to develop a peak ground acceleration map with the kind of things that my colleague from Myanmar has spoken. And so we have developed the peak ground acceleration map for 475 years. Because the normally buildings are designed for 475 years, which means that there is a 10% chance of having an earthquake in the next 50 years. And based on that, the peak ground acceleration map is shown up here. And then the peak ground acceleration map is to be converted into intensity. I must mention here that the earthquakes normally are identified by the magnitude. But the magnitude is very important, but the magnitude is a constant number. Whether you have felt the earthquake or not, it was a 7.7 magnitude earthquake. But in different parts of the region, you will feel intensities differently. So the vibration felt in Yangon and the vibration felt in Mendeley are completely different. So that is why we have to have the intensity mapping also, because the damage of the building is dependent on the kind of intensities the building is subjected to. And then the intensities are then converted into some other things which I'm going to talk about here. But intensities are normally measured under the modified Macaulay scale or EMS 98, the European microseismic scale of 1998. They are more or less the similar. And then these empirical, these are converted into PGAs and PGVs, the peak ground acceleration and peak ground velocities, using different kind of methods. These methods have different kind of capacities in them. For Pakistan, we have used Ahmadzadeh and et al. Logarithmic model to develop the peak ground intensities. And this is the peak ground intensities. And you can see here that cities, some of the big cities like Quetta, Islamabad, Peshawar, Kohat, are in the intensity zone of 8 and 9. They are some of the very severe high-level intensity zones. While Sindh and Punjab, including Karachi. Karachi is the largest city of Pakistan. It has about 30 million people, half of Myanmar. And you can see here that Karachi is also can have intensities up to scale 7. All right, now, so we have done the hazard assessment. Now we have to do the exposure assessment. And for that, we need to have a building inventory data. How many buildings are there and what are the purpose of these buildings, how they are used. And then based on that, we have to go and do the vulnerability assessment. For that, we use the Pakistan census data of buildings. Every 10 years, a building census is conducted in Pakistan, and it provides information in a completely different manner, where it identifies the roof material, the wall material, and then we have to come up with a strategy to convert them into a built environment strategies here. And this is what we did. We look at the possible combination and permutations. A reinforced concrete roof cannot be supported on brick method or on adobe walls, things like that. And based on that, we have come up with this strategy that there are actually 7 types of buildings in Pakistan in general: the stone masonry, adobe, brick masonry, wood and timber, block masonry, and other masonry, which are like shanty lands, small dwellings. And then for reinforced concrete, we have divided this category into 3 categories, which are low rise, medium rise, and high rise. And you can see up here that the proportion of these buildings here, M5 is the brick masonry building here, and about 40% of the buildings are M5. The strange thing that you will notice here, that the RC buildings here is about 27%. A quarter of the buildings are reinforced concrete, and only God knows how many of them are engineered. But let's say all of them are engineered. The remaining 75% of the built environment in Pakistan is non-engineered. And I won't be surprised to have a similar number for the neighboring countries also. I won't be surprised. Nepal, I'm sure, is no different. India is no different. So is Myanmar, so is other countries also. And this is where the problem lies. And then we have compared these things with the European standards. And based on these things, we have developed the vulnerability indices. This is a statistical method through which you can develop the vulnerability indices here. And you can see that some of the buildings, like other buildings, are very vulnerable. But these numbers are not very different from each other. So whether it is reinforced concrete or not, the vulnerability is still very high because of several other reasons, which I don't want to go into right now. Now, the damage matrices have to be developed, and they have to be mapped against the MMI scale or EMS 98 scale. And then the damage probability matrix is based on these 5 category of damages from D0 to D5. There are 6 categories. You can see here that D0 means no damage at all, to D5 means total destruction, and they are beyond repair. But to me, the interest is in D3 and D4. These are the buildings which have undergone either moderate structural damage or some heavy structural damage, but they can be repaired. So these are the areas. If this is the category, then there's no point. We just demolish it. But these are the D2, D3, and D4, the categories which are within the repair conditions, and they can be repaired. And then based on this thing, this is the probability distribution, which is called the fragility functions. So these are the fragility functions. Oops. I'll just explain one of them. If you look at this thing here, this is the intensity scale from, it's from 0 to 12, but obviously anything less than 5 is not worth mentioning. And these are the 5 different damage matrices here: D5, D1, D2, D3, D4, and D5. So if there is an intensity of 8 magnitude, sorry, not 8 magnitude, the intensity of 8 scale, the probability of damage of wooden and bamboo structure will be something like 5% or maybe 4%. But if it is a 9 intensity earthquake, we're talking about something like 15% of damage. So 15% of buildings will undergo complete collapse. And then depending on the intensity, you know, some of the areas in Myanmar faced up to 11 intensity. So that is why this can go up to 8. Then a similar fragility functions for the stone masonry, for adobe, for brick masonry buildings. And these are all the pictures that I took myself, the buildings that we have here. Then the block masonry buildings. And I reckon that the built environment in our part of the world, Asia and South Asia, is not very different, unfortunately. And then these are low-rise RC buildings. Then there are medium-rise RC buildings, and there are high-rise RC buildings. Anything which is 10 and above is, in our definition, is a high-rise building here. This is the building right in front of the university that I used to work, and this is a 19-story building. Then there are these buildings, which are very, very difficult to quantify, but we have these buildings, unfortunately, quite a big in number. I think about a little more, around 2% of our built environment. In Pakistan, there are about 16.6 million buildings. So 1% is about 166,000 buildings. So it's still a very large number. And then based on these, the analysis that I've shown here, this is the damage probability matrix here in different regions of Pakistan, Azad Jammu and Kashmir, then we have Balochistan, then we have federally administered tribal areas, Islamabad, Federal Capital Territory, Gilgit-Baltistan, Khyber Pakhtunkhwa, Punjab, Sindh, and the grand total here. And then you can see here the total building are at risk are 128,000 buildings here, and this shows the proportion. And then obviously D5 is about 30,000. Similarly, for adobe, we have a similar number, but you can see here the number of buildings of adobe is 6 million. Similarly, for brick masonry, and then followed by wood, and then followed by block masonry, followed by the low-rise RC buildings, followed by medium-rise and the high-rise here. After doing all these things, we ran through the 2 different scenarios, that if an earthquake of the previous 2 earthquakes, which I've mentioned here, if that earthquake repeats itself, then what will happen? And this is the 7.6 magnitude earthquake of Kashmir and Hazara that took place on the 8th of October 2005, where 73,000 people died. And this, this is the intensity distribution map. This shows the rupture of the fault that took place here. And these are the damages. And you will be surprised to know that the number of damages that we estimated are around 2% less than the actual damage. So this is how accurate the results are, unfortunately. I mean, obviously, nobody would like to have an earthquake, but I'm just telling you how reliable these models can become depending on how you train them and how accurate you collect the how accurately you collect the data from the damaged buildings. And then this is the special distribution of the buildings in that particular area. And you can see the damages, 71,000 buildings completely destroyed because this is D5 earthquake. But if you count these three things here, this is 20,000, 35,000, and 44,000. So they account for the buildings which could be retrofitted, which could be restored with either very little effort or with some effort. And this is what we should try and focus on, these three categories. We must not worry about these things. Obviously, they are the killers. As somebody, one of my very close friend who is a professor at the University of Colorado Boulder said that these buildings are the weapons of mass destruction. Unfortunately, but these are the weapons of mass destruction, 71,000, and they are the killers. And if we pick them early, we can use the retrofitting techniques which our colleagues from Bangladesh has identified, and then we can improve our quality of built environment. Similarly, this is the 2013 earthquake of September 16th in Avaran, the province of Balochistan. As I told you that this was a less populated area. However, you can see here that that the number of buildings are 91 which are beyond repair. However, I would say this is 10,000, 3,000, and 1,000 here. So these are the buildings that could be repaired. And I'm so proud to tell you that we repaired the buildings, adobe buildings, made them earthquake resistant, and the project was awarded. The project awarded in ACECC, CCAR 8 in Tokyo. So we actually saved about 50,000 buildings. The conclusion is that Pakistan faces a significant challenge, which necessitated the comprehensive assessment of the risk built environment. We need to have more accurate data about buildings here. Adobe and brick masonry buildings remains the most vulnerable buildings because the majority of them undergo damage between D3 and D5. And obviously, GIS-based planning and disaster management techniques could be used. And finally, the emphasis must be that the policymakers must understand the importance and must take the decisions according to the assessment here. The way forward is the regularly updating the building databases, then promote earthquake resistant construction, enhance GIS risk assessment tools. As my colleague from Myanmar has mentioned, GEM. I don't know whether Myanmar is part of the global earthquake model, but if it isn't, I would encourage you to take the membership. There's a tremendous help that comes from GEM. I've had an opportunity to work with GEM for a lot of years before I turned into an administrative clerk. And then develop public awareness, because the safety is extremely important, and people are conscious of the dwellings and the houses they're living in, then they will take care of the seismic resistance by themselves, because the majority of buildings are not owned by the government. They are privately owned. And you cannot force a private owner unless they're willing to do it. And then you can develop an insurance mechanism, you can develop some loaning mechanism to improve the building, because eventually this is going to add value to the building that they are reliving in. And then strengthen the policy framework for infrastructure planning. And I've just talked about buildings only, but the similar things could be done for bridges, for dams, for other infrastructure. And encourage interdisciplinary collaboration between government, research institution, and urban planners. With this, I thank you all. I must apologize. I was very quick because I was mindful of the fact you have only 2-3 minutes, and I can take a few questions, please. Oh, it's difficult. There are two ladies, so I'll wait. Yeah. Thank you. Kindly introduce yourself.
Hello, I'm Asi from Indonesia. It's a very, very interesting presentation, and you basically went through like it's exactly our problem that a lot of the maybe majority of the buildings in countries like ours are non-engineered, and it's very difficult to manage them. So actually one of the biggest tasks in doing something that you did is the data sets. And I noticed that you were talking that there's a census, every 10 years or so, where you can get like the data set for the building typology. So I was wondering how accurate those data are.
All right.
And then also especially like I guess challenges in actually obtaining data sets if there are any. In terms of the earthquake data sets itself, I can imagine that it's more easy to estimate, but the buildings themselves are the most difficult to actually establish. Then more so the second question would be that I see that your what you call it, like you have the vulnerability index, and I know that the EMS actually establishes those, but typically sometimes they're different between what EMS has as a risk and then what is actually happening in different local conditions. So do you account to these maybe differences, even if it's adobe, maybe adobe masonry in area A and B can have different structural quality, therefore different vulnerabilities, and do you account for that?
Okay.
And if so, then how do you get the data for that? Thank you.
Okay. The first question is actually a very tricky thing to do. Building a reliable building inventory. That's the most difficult thing. So what we did was that we first of all used the building census data, but the building census data was not intended for that purpose. It was a different purpose. So we got the data, but then we have to do the ground truthing also. So the easiest thing was I put in a few of my students who downloaded the photos from Google Earth. So we had the coordinates of that particular building, because a lot of people put up the pictures of their houses and buildings. And there are hundreds and thousands of buildings that could be downloaded. And through expert opinion, you can identify their types, whether it is brick masonry, block masonry, and obviously the regions also, we know where the construction is going to take place. So then we did the ground truthing towards that. And then we had conducted detailed survey of some of the major cities also. We've taken the pictures, we have taken the videos, converted the videos into a building inventory, and then cross-checked it and benchmarked it against the building census data. It took us 5 years. And there was a funding also available for this project. And I mean, obviously the Pakistan share was not 5 million euro, but from 2011 to 2017, Pakistan was involved in a project called Earthquake Model for Middle East, which eventually became the part of GEM. And through that, we had some funding available. I think, if I am not wrong, I'm talking about 200,000 euros. So it was enough for us to travel around the country, collect the data, undergo training, all those things. That's the first thing. The second thing, that the question that you asked, is about the EMS. And localization of EMS is another very, very difficult thing. So we haven't done the localization or nationalization of EMS, but I think EMS is broad enough to actually, because it is only identifying the intensity scales based on the observed damages over the last several decades. So it's quite reliable. Yeah. Yeah. Thank you, ma'am. And I'll take the lead from Uday, and we're not going to pass 3:30. So you have to be very quick. All right, thank you, sir. You are a generous man. Thank you.
Okay, thank you very much for your insightful presentation. I clearly learned that as you said that there is the difference in risk factor depending on the type of buildings, type of construction. So in the case of our country, with recent earthquake, we first realized that the RC buildings are more dangerous than funicular lightweight structure building, which can withstand more the lateral force. But in reality, their funicular building in Inle Lake, they all affected seriously. So after the damages, there'll be reconstruction of the whole cities and towns. And so I'd like to know if there is any advice from you, which types of buildings could be more suitable for like urban area, or in rural area like mid-rise or no more RC building, or if there is any advice from you, we like to know. Thank you very much.
Thank you, ma'am. You see, I'll be making a presentation, a very quick presentation tomorrow also about the sagging earthquake that we had, unfortunately, about 2 weeks back or about a week back. And I have done a very crude risk assessment also because I didn't have the data, but actually I can indicate a few things. So that'll give you an insight of how this risk assessment could be done for Myanmar, and then we can benchmark it to the existing damages and then improve our models. As far as the vulnerability of the buildings are concerned, you see the vernacular architecture, the number of occupancy is always very small because it's never several stories high. So people living in them is always a small number as compared to a reinforced concrete apartment building, which could be 5 stories, 6 stories, having 200, 500 people living in them. And our family sizes are very, very large. I don't know what the average family size in Myanmar is, but in Pakistan, the average family size is something like 9. And I won't be surprised if the number is similar. So in an apartment building, that's why they are vulnerable. And that is what we have to identify. And as a policymaker, we have to make sure that what are the directions that we are going to take in. This is not going to be one size fits all. It has to be on a case-to-case basis. It has to be on an importance basis also. I mean, the way you retrofit hospitals will be different than the way you retrofit the residential buildings, because these are the essential facilities. So this all depends on the performance-based codes that is normally adopted by the world, whether you're looking for life safety or where you're looking for immediate occupancy. These are the different kind of performance levels which the building codes identify. And an immediate occupancy is a facility where you actually would not like any structural damage and they should be ready for use right after the earthquake. But then it's not that simple, unfortunately, because then you have to look at the non-structural elements also. A hospital building may be safe, but if the oxygen pipeline breaks, or if the refrigerators storing blood falls, topples over, or if the electricity or the water supply breaks down, then the building's of no use. So we have to look at the whole thing in a much larger scale. And that is why you cannot stop earthquakes from happening. But if careful planning is done in a long-term basis, then we can mitigate and reduce the risk to a certain level. And then all depends on how much of risk that we want to mitigate and what is the level of risk that we are prepared to take, because that involves a lot of money, a lot of time, and a lot of capacity. Because as human beings, we forget things very, very quickly. We had a massive earthquake. 73,000 people died only 20 years ago. Sorry, we haven't learned the lesson. We're back to what we were. So, it has to be done from the policymaker, from the individuals, from the responsible people, and the society together to come up with a mix. I hope I've answered your question. Thank you very much. I would like to thank all of you once again for being here. And I will leave or close the session with only one thought. 16 out of 17 member economies are highly earthquake vulnerable. And the only way to reduce the risk is to collaborate and do some collective thinking together. There are so many other committees also, but TC-22 is the right time that we would love to have participation from the other partners in ACECC. Thank you very much.